All right, this is homework for Chapter 7. Intersection of hospital hallways, a convex mirror. Remember, a convex mirror looks like this, where the person or the object is on this side of the mirror. It's like a security mirror. It's mounted high on a wall to help people avoid collisions. It has a radius of curvature equal to 0.45 meters. And so the focal length is half that, but for convex mirrors, the focal length is negative, so it's 0.45 over 2. 0.225 meters, negative 0.225 meters. Locate and describe the image of a patient 15 meters from the mirror, and then also determine the magnification of the image. So I want to find Q first. I know from the mirror equation 1 over F equals 1 over P plus 1 over Q. Like that. So that's 1 over negative 0.225 minus 1 over 15 to the negative 1. That gives me an image distance, Q, equal to negative 0.22 meters. Negative 0.22 meters. We can find the magnification, negative Q over P. Gives me a magnification of 0.015. All right, so now I can describe this image. It's virtual. It's virtual because Q is negative. It's upright. Upright because M is positive. And it's smaller than the object because the magnitude of M is less than 1. A concave spherical mirror has a radius of curvature of 20 centimeters. Locate the images from object distances of 40. Actually, I changed this, 40, 10, and 5 centimeters. A concave mirror looks like this. My object is over here. It has a positive focal length. The focal length is the radius of curvature over 2. So that's 10 centimeters. That's just half of this number. And now I want to locate the images, find the magnification, and describe the image just like I did before. For P equal 40 centimeters. So my image distance then is 13.3 centimeters. For when my object is at 40 centimeters, I can find my magnification, negative Q over P. And that is a magnification of negative 0.33. So this is a real object because Q is greater than 0. Q is positive. I have a plus Q. It is a inverted because I have a negative magnification, and it is smaller because my magnification is less than 1, my magnitude of the magnification. All right, now P equal 10. Q is equal to 1 over F minus 1 over P. That's just solving the mirror equation for Q. 1 over 10 minus 1 over 10 to the negative 1. It's 1 over 0. That's not defined. There is no image when the object is at the focal point. And now finally, part C, when P equals 5 centimeters. That gives me an image distance of negative 10 centimeters. My magnification, is positive 2. So now I have a virtual image because Q is negative. I have an upright image because magnification is positive. And I have a bigger image because my magnification is bigger than 1. Dentist uses a mirror to examine a tooth that is 1 centimeter. So P is equal to 1 centimeter in front of the mirror. The image of the tooth is formed 10 centimeters behind the mirror. So Q is negative 10 centimeters. Determine the radius of curvature and the magnification of the image. So I want to know what is F. I can find the magnification of the image. That's easy because I already have it. Negative Q over P. That's going to be negative 10 over 1. So my magnification is 10. That's for part B. And I also want to know what is the radius of curvature. So I need to find the focal length. 1 over Q plus 1 over P. That gives me a focal length of 1.11 centimeters. Notice that this is positive. That means that it's a concave mirror because that has a positive focal length. And so the radius of curvature is twice that, which is 2.22 centimeters. Doesn't make sense for a dentist to use a convex mirror because a convex mirror will always make the image smaller than the object. So this is part A. A 2 centimeter high object is placed 3 centimeters in front of a concave mirror. All right, so the height of the object is 2 centimeters. P, the object distance, is 3 centimeters. If the image is 5 centimeters high and virtual, so the height of the image is 5 centimeters. And this virtual means that Q is negative. If Q is negative, that means that M, which is negative Q over P, has to be positive. So if Q is negative, that means that M is positive because this term would be negative, making M positive. So I can say then that my magnification, actually I'm getting a little bit ahead of myself. So, So my magnification then is height of the image over the height of the object. That's 5. My magnification is 2.5. And I know that it has to be positive because it's a virtual image. And a virtual image is going to be upright with a positive magnification. All right, so I want to know the focal length. I know P, and so F would be 1 over P plus 1 over Q to the negative 1. Since I know the magnification, I also know that the magnification is given by negative Q over P. And so I can solve this now for Q. So Q is going to be negative MP, negative 2.5 times 3, which is negative 7.5. So that's my Q. Now I have everything to find F. 1 over 3 plus 1 over negative 7.5. Inverse of that. That gives me 5 centimeters. And that's the answer. Notice it is positive, so it's a concave mirror, but that was stated in the problem. A convex lens has a focal length of 20 centimeters. Remember, a convex lens looks like this. It has a positive focal length, so F is plus 20. I want to know the images for these object distances, and for each case describe the image and find the magnification. So for P equal 40, this is very similar to what we've done before. I'm just going to find Q. It's 1 over F minus 1 over P to the negative 1. So Q then is equal to 1 over 20 minus 1 over 40. So for part A, Q is 40 centimeters. All right, my magnification, negative Q over P, is negative 1. So this is a real image because I have a positive image distance. It is an inverted image because my magnification is negative. And it's the same size as the object because my magnification equals 1, or the magnitude of my magnification equals 1. Second part of this was, what if P equals 20? All right, well, P equals 20 and F equals 20, so you can probably say right off that there is no image, but let's just show that Q is 1 over F minus 1 over P to the negative 1, which is 1 over 0. So there is no image because 1 over 0 is undefined. And P equal 10. Q is 1 over F, that's 1 over 20 minus 1 over 10. And so that gives me a Q of negative 20. Magnification, negative Q over P. Plus 2. So I have a virtual image. Virtual because Q is negative. I have an upright image. Upright because M is positive, positive magnification, and it's bigger because the magnitude of M is bigger than 1. It's twice as big, in fact. Where must an object be placed to have unit magnification for a convex lens of focal length 12 centimeters and for a concave lens of focal length 12 centimeters? All right. So first let's consider the convex lens. Convex lens looks like this. Now, a convex lens can either have upright or inverted images. So my magnification is conceivably equal to plus or minus 1. So I'm going to consider each scenario. Let's consider first M equal plus 1. All right. If M equals plus 1, that means that the magnification is negative Q over P. 1 is equal to negative Q over P. And then I can also say 1 over 12. That's the focal length. Is equal to 1 over Q plus 1 over P. So I'm looking for P. So I'm going to solve this equation on the left for Q. So Q is equal to negative P. And then I'm going to substitute this in for Q. 1 over 12 equals 1 over negative P plus 1 over P. That is not a true statement, so this doesn't occur. Does not exist with a convex lens magnification of positive 1. Just can't occur. So then let's consider magnification equal to negative 1 for a convex lens. Negative 1 equals negative Q over P. And then 1 over 12 equals 1 over F plus 1 over P. Do a similar thing. Here I get Q equals P. And so 1 over, excuse me, I made a mistake here. This should be Q. 1 over 12 equals 1 over P plus 1 over P. And then if I solve that for P, I get P equals to 24 centimeters. So that's where the object has to be in order to have a magnification of negative 1. Now let's consider for a concave lens. Remember, a concave lens is like this. And for a concave lens, the focal length is negative. a concave lens only produces virtual images. Alright, and since the magnification is negative q over p, if I have a virtual image, it's going to be upright. So I'm only going to consider m equal to +1 in this case. So I have 1 equals negative q over p. And I have 1 over negative 12 equals 1 over p plus 1 over q. Here I say q is equal to negative p. And I substitute that in for q. So I get 1 over negative 12. It's 1 over p plus 1 over negative p. But look, the right-hand side goes to 0, so that's not a true statement. So this also does not exist. You can't have a concave lens with a magnification of +1. Right, this is a concave lens with a focal length of 20 centimeters. Remember, concave lens, focal length is negative. This is a lens that looks like this, sort of caved in. I want to know the object distances, just like number 5, but for a concave lens. So let's first consider A, P equals 40. Q then is going to be 1 over F minus 1 over P to the negative 1. That's 1 over negative 20 minus 1 over 40. Gives me an image distance equal to negative 13.3 centimeters. And then my magnification is negative q over p. It's going to be negative 13.3 divided by 40. It's positive 0.333. All right, so that's A. Oh, and so this is a virtual. Virtual because it's negative q. Upright because it's positive m and smaller because the magnitude of m is less than 1. But concave lenses are kind of like convex mirrors, those security mirrors. They're always going to produce virtual, upright, and smaller images. For that reason, I'm just going to give you the solutions for B and C, give you the answers, because they work out exactly the same. For part B, P is equal to 20. Doing the same thing, you find a Q, the same thing as in part A. You get a Q equal to negative 10 centimeters, a magnification equal to negative 0.5, and virtual, upright, and smaller. So ditto, ditto, ditto for these three. And then for part C, you should try these on your own just to make sure that you can do the mechanics of the equations. So here P is equal to 10. You get Q equals negative 6.67 centimeters. M equals negative 0.667. Virtual, upright, and smaller image for the same reasons as part A. Two converging lenses, each a focal length 15 centimeters, are placed 40 centimeters apart. An object is placed 30 centimeters to the front of the first lens. This is a two-lens system. Draw an axis first, an optical axis. I have one lens here, another lens here. Focal lengths are here, here. They're separated by a distance of 40 centimeters. And the object is placed 30 centimeters in front of the first lens. So let's see. The object is right here. All right, this is P. I'm going to call this P1. F1 is equal to 15. And F2 is also equal to 15. Okay, we're going to treat each lens separately, taking the image from the first lens as the object for the second lens. I'm going to take the first lens here. I'm going to find Q1. So Q1 is equal to 30 centimeters. M1, the magnification due to the first lens, is negative Q over P. It's equal to negative 30 over 30, which is negative 1. All right, so my image from the first lens is going to be 30 centimeters to the right of lens 2. Let's see, 30 centimeters. This isn't exactly to scale. I'm going to put it right about here. All right, notice that I draw it inverted. This distance is Q2. It's equal to 30 centimeters. Notice that I drew it inverted. That was because the magnification was negative. I also drew it the same size as the object, but inverted, because the magnification was equal to negative 1. Now, this image is going to become the object for lens number 2. So this is going to be my object distance. P2 is going to equal 40 minus 30, which is equal to 10 centimeters. So P2 is going to equal 10 centimeters, and now I can find Q2. That's 1 over 15. Let me write this out. 1 over F2 minus 1 over P2 to the negative 1. That's 1 over 15 minus 1 over 10. That gives me the image distance, which is negative 30. Means that the image from the second lens is 30 centimeters to the right, or excuse me, to the left of the second lens. Let's go and find the magnification for lens number 2. So the image is going to be in the same direction as the first object and 3 times as big, and 30 centimeters to the left of the second lens. So the second image is going to look something like this, where this distance is 30 centimeters. Notice it came out negative, so it's to the left of the lens. And it is in the same direction as the object, that is to say it's inverted, and it's 3 times as big as the second object. So now if I want to know the total magnification, that's going to be the product of the 2 magnifications. Negative 1 times positive 3 is equal to negative 3. So this image has a magnification of negative 3 when compared to this object. It is inverted from that object and 3 times as big. Find the image of this object next to a flat mirror. Draw at least 2 rays. We do this in lab, but I know not all of you are in lab. Looks like this. You draw 2 rays. Here's the first. Follow the law of reflection. That is, this angle has to equal the reflected angle. I'm just going to draw it best I can. Like that. So those 2 angles are equal. Then you draw a virtual ray. This is a ray that extends back from the reflected ray. Now I'm going to draw a second ray, also through the object. See, around this object, there are rays emanating in all directions. Right? And these rays, or these lines that I'm drawing, just represent light waves that travel along these lines. Now I'm going to draw the reflected ray, following the law of reflection. It's going to look something like that. I'm going to trace back what we call the virtual ray. These 2 angles are equal. where these two cross is where my image is. That's pretty good. In lab, you use a protractor and you do this more rigorously. This is my object distance. This is my image distance. Remember, for flat mirrors, P was equal to negative Q. Okay, now for the ray diagrams for the lenses. The ray diagrams for the mirrors, we have several rules. The first rule, the first ray, we're going to draw parallel to the axis and through the focal point. The second rule, through the focal point, parallel to the axis. The third rule, let's do it in black. The third rule, we'll do through the center of curvature and back. I'll show you what that means. And then the fourth rule, to the center of the mirror, and let theta I equal theta R. Follow the law of reflection. The law of reflection is going to apply for all of the rays, but at the center of the mirror, it's easier to see it. So we'll use that just as a fourth ray. On the quiz that you'll just have to show 3 rays, but you need to be able to draw all 4 for the exam. All right, so the first one is parallel and through the focal point. Parallel to the axis through the focal point. That's number 1. Number 2 is through the focal point and parallel to the axis. All right, I already know now where the image is going to be. It's going to be where these 2 rays cross. But let's go ahead and do the others. Through the center of curvature and back again. It's going to draw a line through the center of curvature. It's going to come to the mirror, and then it's going to reflect back on itself. And then finally to the center of the mirror and follow the law of reflection. That's number 4. This is number 2. And this is number 3 ray. My image is here. It looks like this. All right. That is a real image. It is inverted, and it appears to be smaller than the object. All right, I'm just going to be able to draw a couple for this one. Let's do parallel to the axis and through the focal point. This is when the object is at the focal point. If you recall from the homework problems, something funny happens here. That is that there's no image at all. That's number 1. I can't draw number 2 because it's sitting at the focal point. So I'm going to do through the center of curvature and back again. That is, I'm going to draw a ray up such that if I were to trace it back, it would go through the center of curvature. So I draw it up, and then it reflects back on itself. This is number 3. And then I can also draw number 4, but it's not really necessary. I see that these 2 rays are parallel. And parallel rays never cross, so there's no image. Because all of these rays, these 3 rays, are all parallel to one another. They're never going to cross, neither on the real side, nor if I were to trace them back, they would never cross on the virtual side of the mirror either. All right, parallel to the axis through the focal point. That's number 1. Number 2, through the focal point and parallel to the axis. This one's a little trickier because I'm inside the focal point. It's going to look like this. I'm going to draw a ray up, such that if I were to trace it back, it would go through the focal point, and then it goes parallel to the axis. It's number 2. Number 1, number 2. Now, number 3 was through the center of curvature. Now, actually, let's go ahead and do this, because I can see now that these rays are diverging. That means they're never going to cross on this side of the mirror. So I need to draw back the virtual rays for each of these. I'm just tracing back the reflected ray. Now I know where my object is going to be. It's going to be right here. Alright, this is like a shaving mirror holding it up really close to your face. Now I'm going to draw in these third and fourth rays. As soon as I get 2 good rays that I know, I like to draw in the third and fourth rays. Through the center of curvature, I draw a ray such that if I were to trace it back, it would go through the center of curvature, and then it reflects back on itself. I'm going to go and draw in the virtual ray as well. Right, but that's all a single line. This is number 3. And then number 4, to the center of the mirror, and then reflected back using the law of reflection. I'm going to draw back the reflected ray. This is a virtual image. It is obviously upright, and it's bigger. Alright, this is a convex mirror. There's only one scenario on this. Remember, the convex mirror always produces virtual, upright, and smaller images. I'm going to go parallel to the axis and through the focal point. Parallel to the axis. And then the ray is going to be reflected away like this, but it's going to be reflected in such a way such that if I were to trace it back, it would go through the focal point. I already know that this is going to produce a virtual image, so I'm also going to go ahead and trace back my virtual ray. Or something like that. It should go through the focal point. That's number 1. Number 2 is through the focal point and parallel to the axis. So I'm going to trace a ray. It goes like this, such that if I were to trace it forward, it will go through the focal point and then parallel to the axis. Notice that ray number 1 and ray number 2 are divergent, so that's how I know I have a virtual image, but I knew it already. And so my image is going to be right here. I'll go ahead and write it in. So remember, this is like a security mirror, so I'm looking upright and smaller. Let's go and draw in our other rays. Through the center of curvature and back again. It's just one big long line. Trace a ray, such that if I were to trace it forward, it would go through the center of curvature, and then it would let it reflect back on itself. Then I'm going to trace forward my virtual ray. It looks like that. And then finally, number 4, to the center of the mirror. I'm going to trace back the virtual ray. They all cross at the same point. As we said already, this is virtual, obviously upright, and smaller. It's like a security mirror. Alright, in a similar way, we're going to have rules for lenses. They're very similar. 1 parallel to the axis through the focal point. 2 through the focal point parallel to the axis. 3 through the center of the lens. This is a little bit different. The first two are the same, but through the center of the lens, unrefracted, unbent, straight through. I'll show you what that means. All right, first one is parallel, and then through the focal point. That's number one. Number two, through the focal point, and then parallel to the axis. I know then that my object is going to be here, or my image rather. It's going to look like this. It's inverted. Appears to be smaller. It's real. It's going to draw on that third ray right through the center of the lens, unbent. I have a ray that starts up here, goes all the way through. I'm sort of messed up there at the end. All right, that's number three. They all cross at the same point. Real image, inverted, smaller. Here my object's at the focal point, so you can imagine what it's going to be. Going to be no image at all. Parallel through the focal point. And then through the center of the lens. I can't draw the second one because it's at the focal point. Those two rays are parallel, so there's no image. In fact, you know, I could draw in any number. I mean, there aren't really rules, but look, I could draw in another ray here, and it would also be parallel. All those rays are going to be parallel to one another. No image. And so these questions are moot. This was ray number 1, and this is ray number 3. The red one isn't ray number 2. I was just drawing it as just sort of an extra ray. All right, this one's a little trickier. Parallel to the axis and through the focal point. Now through the focal point, that's number 1, and parallel to the axis. So I'm going to draw my ray such that if I were to trace it back, it would go to the focal point, and then it goes parallel to the axis. That's ray number 2. All right, notice that these two rays are divergent, so I need to trace back these from my virtual rays. I'm going to have a virtual image. My virtual image is going to be right about there. I can draw another ray through the center of the lens and then trace it back. Shows me where it is. This is ray number 3. One more. Parallel to the axis through the focal point. This is probably the hardest of all of them. It sort of changes up a bit. Parallel to the axis. Now I'm going to go through the focal point, but I have to go through the focal point on the left-hand side. This is a diverging lens, so it's going to cause my rays to diverge like this, such that if I were to trace them back, they would go through the focal point like that. And I've drawn the virtual ray already. That is the ray, the refracted ray traced back. It's number 1. Number 2 is through the focal point and parallel to the axis. Now I'm going to draw it through the focal point on the right-hand side. Draw a ray such that if I were to trace it forward, it would go through the focal point. And now it goes parallel to the axis after it goes through the lens. I'm going to trace back the virtual ray, and then tells me that my image is going to be right here. So it's going to look something like this. Then I can do one more ray just through the center of the lens. It's going to look like this. This is number 3. This is number 2 right here. Let's see, this is a virtual image. It's upright and it's smaller. I don't know if I did this up here. That was a virtual, upright, bigger image. That's the end.